Hello again. So here we are in lecture 5 on sequences, and we're going to talk about some sequences to plus or minus infinity, whose limits are plus or minus infinity. This should be a short lecture, but let me just point out these two theorems here showed up in previous lectures, right? If really your sequence is defined as the restriction of a real valued function, and that real valued function has a limit, then you can find the sequence limit that way. And then there's the squeeze theorem. If your sequence is squeezed between two sequences you know the limit of, then you can find the limit that way. So what can we do with this? So let's look at another sequence. Let's look at the sequence. Oh, let's make it simple. Let's just make it n. N equals 1 to infinity. Well, what's happening here? This is the sequence 1, 2, 3, 4, 5, right? We could go on forever if we wanted to. Can we say that limit as n goes to infinity of this particular sequence is any finite number? No, it's not. What's happening here is this is just getting bigger and bigger and bigger and bigger. That limit is what we say is positive infinity. So the limit as of a sequence, so let's write this down, the definition informally. We say the limit as n goes to infinity of a sequence an is equal to positive infinity if the an's get bigger and bigger and bigger. Bigger and bigger as n goes to infinity. That works pretty well. Really, you want to add a little bit arbitrarily bigger, so as big as you want it to get. So you've got some things getting bigger and bigger and bigger, but never get past a certain point. But you want this to not be bound by any certain point. So the formal definition of this is limit n goes to infinity of an is equal to infinity if for every real number b there exists some capital N, so that whenever little n is bigger than capital N, a sub little n is bigger than b. So does that work up here? Let's just say b is equal to, a million. Exists a point in the sequence so that when I'm past that point, my elements in the sequence are bigger than a million? Yeah, it is. What would my capital N be? Well, in this particular sequence, my capital N would be a million, right? If little n is bigger than capital N, then little n is bigger than b. A sub little n is bigger than b, and we've got it. So this clearly, we can say it diverges to infinity, but it's sort of a way of converging. Okay, and the thing to notice here, the reason I have these theorems here is because, in fact, these theorems hold if you switch this finite L with infinity. That's perfectly reasonable. If this f of x goes all the way up to infinity, the an's have to go all the way up to infinity too. And the squeeze theorem, we can actually make sort of a slightly weaker hypothesis. Yeah, of course, if something's squeezed between two things that are going to infinity, it's got to go to infinity as well. But actually, for the infinity thing, we can actually just think of it bigger than something else going to infinity and ignore that thing it's less than, right? If it's bigger than something else going to infinity, it's going to go to infinity as well. Okay, and Well, of course, then we've also got negative infinity, which is exactly the same thing. So let's just change that. The informal definition of going to negative infinity is that they're not getting bigger and bigger, they're getting smaller and smaller. But again, that's smaller and smaller, it's actually arbitrarily small as you like. So more to the point, it's going to go to negative infinity if for every b there exists an n, capital N, so that whenever little n is bigger than capital N, a sub little n is less than b. So here you want to think of b as a really small number. In the first definition, you wanted to think of b as a really big number. Here you think of it as a really small number. And these theorems work for plus or minus infinity here. And of course, what is the difference here? Here you'd erase the an and keep the cn. So bn is less than something going to negative infinity, then bn has to go to negative infinity as well. So this was infinity. And now we can say negative infinity. Okay. And I just wanted to get a quick note that talk about limits to infinity as well.